All right. Uh, I welcome everybody to this presentation, and this presentation is on developing a method for detecting volatiles in dog urine. My name is James Theodore Anderson, and this project was created in collaboration with Dr. Paul House. And those are some pictures of my dogs. So, who am I and why am I here? I am a senior in the chemistry program, and I have been working on this project for almost 2 years now, and that gives me a little bit of, I would say, reason to be talking about this project, as I know this is going to be going up on YouTube for future students that are going to be interested in it. My main focus on this project is, and will be, and was be, uh, going to be focusing on quantitative analysis for this project. So turning all of the peak areas and all of our data into usable quantitative data. So the objective is to develop a quantitative method for determination of volatiles in dog urine. Volatile compounds are pretty important in olfactory communication between dogs. So like between smelling, there's what she did is she would collect dog urine, Dr. Osberg would, and she would paint it on sticks or stakes, and then we could tell by the dog's base tail position that there was communication going on. But in terms of in the field of chemistry, there was not a whole lot of work done, and we don't know a lot about what chemicals are actually in play here. The problems is there are some critics of the solid phase analysis microextraction. There are some critics, and I am trying to determine whether or not the method is actually truly quantitative, and whether or not it could be applicable for our project. And if it is, how do we do it? So a little bit of background is it was a collaboration with Dr. Lispik from the biological sciences. She's who we're getting our dog urine from, and she's the one who got us interested in analyzing what olfactory communication compounds there may be. So what got me and me specifically interested in using solid phase microextraction, or SPME-HS, because we're looking at the headspace, um, is a cockroach video where we put the little fiber into the headspace. So in the cockroach example, the sample would just be a bunch of skittering cockroaches. We would put the fiber above the cockroaches, and you would be able to see what pheromones were being used, like what compounds were being used as they got excited or scared or whatever cockroaches feel when they're trapped in a jar. And that little YouTube video was very interesting to me. And when Dr. House showed me it, I got very interested in it. So and then there's a little picture behind my little head bubble here. It shows that what it basically is it's just a sample headspace, and then stuff evaporates into above the headspace, and that's what we're looking at. And that leads me into what exactly is solid phase microextraction of the headspace. So it is an absorbent polymer fiber. So it is like a CAR, DVB, PDMS is what I'm using. It is just a fiber that molecules can stick to, and then we can release them later through heat. And as the whole method shows, is we put the fiber in, we expose the fiber sticks molecules, we release the fiber out a little bit, and then we move it to the GC, and then we push it back in, heat it up really hot, and it falls off, and then it goes through the it goes through the GC column to the whatever detector it's been attached to, which in my case it was usually a flame ionization detector. But for future students working with dog urine, it will actually more than likely be the mass spectrometer. That is more useful for determining actual like masses and sizes of, and like how the fragmentation patterns can be used to determine what molecules are actually being detected and in what concentrations, relative concentrations. And the reason why this method is really useful for us as well is because it's really sensitive. It can detect uh, parts per billion reliably, and it can also is very good for detecting volatiles, because if we just ran the dog urine, we would get all of the molecules, but with solid phase microextraction of the headspace, we're only being able to detect primary components that are in the smell, which is volatile components. And it is relatively simple. Purge and trap and liquid to liquid extraction, with liquid to liquid extraction being the primary alternative. It uses organic solvents, which are not only dangerous environmentally, but they are also not real great for anybody to work with if you have to work with it, because they are quite toxic and often carcinogenic. So if you can avoid using organic solvents in exchange for just having to use a fiber, that would probably be better. It is a simple process because of that. It just relies on equilibrium constants, like a liquid would too, like how it would prefer to be in one liquid over the other. It just uses that. It uses like how the chemical potential would push it up into the headspace, and then from the headspace, some of that will want to go to the fiber in an equilibrium, and then we can detect that later. Uh, boo, 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 boo. So the next thing is, this is a couple pictures I have of an SPME fiber slash file. The top picture there is fiber holder 3. That's the one that I worked with. It contains the DVB car PDMS fiber. It shows the whole assembly there. There's the black fiber holder and then the assembly that's screwed into it. And then on the bottom left here, we see that there is some amber vials. That's what I use for this experiment. There's the amber vials with the little spin bar at the bottom that contains 2 milliliters of liquid, and I believe those are 4 milliliter amber vials. And then the zoom in on the right is just of how small that fiber actually is. It is very small, 50 to 30 microns. There's a 50 micron coating and a 30 micron coating, so it's incredibly small and incredibly fragile. Very easy to break. So let's talk a little bit about the procedure. So first step of the procedure would be to obtain the sample, and this would be either done with Dr. Lisberg, who from the Biological Sciences Department could provide us with some samples, or for me, or if you're working on this aspect as well, you could be using calibrated mixtures. Like for me, I put in a known amount of 3-octanol into water, sometimes beta-adenone, and then I would sample that and then relate that to a peak area, and then try to get consistent peak areas after that. And then if this happens reliably and we get reliable data, that can result in us moving forward with the project, because we'd be able to tie concentrations to compounds present in dog urine. But so, in the next step after we obtain the sample would be to prepare the sample. This is adding salt and or spiking the sample. This step is pretty picky as well, because there's some adjustments that could be made to either the salt concentration or the pH. Add addition of the stir bar, either concentrating or diluting the sample. All of that can happen here, and we need to be able to reliably account for all of the changes here, because changes here can affect the final concentration. Also temperature needs to be controlled very, very well. And that leads me to the adsorption step. This is where the actual sampling happens. This is where the molecule, when we expose the fiber, as in that image shows, we expose that fiber to the thermostatic system, and then that provides the fiber time to absorb those molecules. This is a very temperature sensitive process that can take between 10 minutes or several hours to several days, depending on how long you want to run it. It all has to be done consistently. You have to keep a same amount of time, temperature, and like fiber depth, all of the same during this step, because small variations can result in great variations in the final peak areas, which means that your calculated concentrations will be very, very different from what you expect. Next step is to desorb the samples. This can be done in the inlet of the GC, which is pretty easy. You just, as it's called, baking the fibers off. You just put them in the inlet for about 3 minutes, and then all of the molecules that were attached kind of just slide off. And then they are pushed through the column, and based on the retention times, how long it sticks in the column, and how fast they go through the column, and based on how much we're able to detect, what like peaks we're getting, or like how much it detects, we can give you a relative idea of what is there and in what concentrations. We use the flame ionization detector, or at least I did, because it gives concentrations, and it's a little bit easier for us to run, because the mass spec requires a new septum after every use. Otherwise, we leak a lot of helium. The FID does not appear to need to do that, which makes it, I mean, it's not the detector, it's the gas chromatography machine that's coupled to the flame ionization detector. But we are thinking about maybe moving towards using the mass spec more because it does give better, more fragmentation patterns, which is better for determining unknowns, which is what we would be doing with actual dog urine. And that leads me to the next step, which is to actually analyze the results, which is piecing together all the fragmentation patterns, all the concentrations, and all of the retention times to give us a good idea of what compounds are coming off in what concentrations. And that would give us a fairly good idea of what's present in the dog urine and in what concentrations, and that could result in either breakthroughs or just expanding our field of knowledge in general for as the human race who would know more about man's best friend. So that some choices that I've been making throughout the process is whether or not to use 3-octanol or beta-inone. I've been using 3-octanol as my material that I'm testing for reliability because it is more water soluble and it requires less hexane. We were using hexanes at one point as a solvent, but it would always result in a very large peak area when we didn't need it. So I switched over to using 3-octanol because then we don't have to worry about a hexane's peak rather than beta-inone. And then we choose to use the 50-30 micron DVB CAR PDMS fiber. That's 50 microns of DVB and 30 microns of the CAR and PDMS coating, or like that's the width of the fiber on the stable flex. And we chose this particular fiber because it was really good for trace analysis of compounds because it has 3 different coatings. Each one has affinity for different molecules, which makes it real great at just picking up the most material overall, which is what we want. We want to try to get a wide range of molecules because we don't know if the molecule we're looking for is really, really small, if it's really, really big, or if it's polar, if it's non-polar. We're not quite sure at this moment. We're just looking for like what is present, and then we're going to be able to narrow that down with further research. And then we chose the GCFID because it is indeed simpler. There's a lot less steps in terms of like using it. It's fairly straightforward. And also because right now, like I mentioned earlier, the septa doesn't need to be replaced after every use, so it makes more reliably consumes helium at a lower rate than the one that's coupled with the mass spec. And then equilibration is the next big thing. We need to choose how long we want to equilibrate it. We want to choose what conditions we want it to equilibrate at, like whether or not like the agitation. Do we want to increase that? Do we want to increase the temperature? Do we want to make sure that it's fully submerged in a water bath? Do we want to use a sand bath? Do we want to use a thermal well? There's a whole bunch of variables there we could choose and we could change. And this step is what will actually impact the end goal the most, because different conditions, different changes in these equilibrium conditions. Like I said, it's a equilibrium constant based process. So changes in environmental conditions changes the equilibrium constant, which changes the equilibrium and changes our final result, which means that our concentrations won't be as accurate. Next step is temperature. This is the absolute biggest variable that we need to control. We need to lock this thing down tight in order to get good results. So that's why this one got its own, even though it's a big part of the equilibration step, is we need to, temperature at all phases need to be controlled because temperature greatly impacts the end result. And then I said salt because there's a lot of different things we can touch, like salt and pH, and that all has major impacts on the end goal, and a lot of different people who are doing processes on organic material add salt to the things because it pushes the equilibrium constant towards the gas phase, and that increases the amount of analyte that we can get in the end, and which means that we have lower detection limits. So that leads to some potential problems in using SPME for quantitation. Well, to start off, it is an extremely sensitive method. As you can see here, our peak areas are very small, That's might for context, we can easily get like 10,000, 16,000 peak areas odd when we're running more concentrated samples. But here we're only getting like 40, and that peak area relates to be about, I think this one was about 500 to 800, which is not a whole lot, but that is about what we're expecting off the fibers at this point. And then another thing we have to worry about is the fragility of the fibers. These fibers are incredibly fragile and incredibly expensive. Right now, this semester, so this is spring of 2023, I bought a pack of fibers for $627, and it only included 3. And these fibers are quite delicate and need to be handled carefully, and that's not ideal. But they're not going to break under like when they're used correctly. But if you forget to retract them and then you try to pull them out, it can damage the fiber, and then it can end up, as it happened with me, the fiber spinning in your solution, and then you're like, well, I guess that's the end of that fiber's life. So the last thing is the the quantitation method that because there's a paper that I included at the end here and in the little handouts that I have. But there's the calibration for each compound in matrix as a suggested method to combat the fast SPME method, which is just taking a known concentration and then relating it to all the other concentrations. That doesn't take into account matrix effects, which is for people who haven't taken quantitative analysis. If you have multiple compounds in solution, they interact through intermolecular forces, and that can result in lower or higher variation and like higher and lower end detected peak areas because they're interacting and they may or may not like want to come out of solution as much, and that or come out in a solution in greater number of like molecules, which would mean that our end result is going to be different from if that compound was present in a different matrix. So we can't just the paper was arguing that you can't just take one concentration and relate it to all the other ones. And in order to combat that, if we wanted to use the inmate in solution, we would have to do a serial additions method for each compound that we want to know the concentration of, which would mean 3 to 5 different runs for each compound we want. So if we had 16 compounds of interest, we would need to run like 45 or so different runs in order to get a good level of like certainty for all of the concentrations known, like by getting 3 different plots and then linear regressing it down. So here's a picture of my results. As you can see here, this is not great data. It doesn't take a genius to figure out that my data plot is very not concentrated. I would say 790 peak area and 2367 peak area don't really show great like correlation, especially when the average, the best fit, if you want to call it that, drawn here would be trending downward, which is never a good sign. We're expecting it to trend upward. It means that there's a problem in either my method or there's a problem in my data collection. And so that's why this project exists, or my specific work on this project exists. It's to try to fix this issue, and it's try to fix this irreproducibility and this variability so we can really lock down concentrations and know which compounds are actually present in higher amounts, so that way we can relate it back in the end. Dogs who produce more of compound X have asserted more dominance on dogs in general than a dog who produces less, or maybe it's a ratio and stuff like that. So being able to lock down the concentrations of compounds that we suspect being used for communication would be great. So what am I doing now? I am solving that irreproducibility. I am working on fixing that, and as my work has been shown, I've been fixing as much of these problems as I can. I've been trying multiple different methods. I have tried a bunch of different things. None of them have shown a lot of promise, but they have given me and the team a lot of insight into what can be done to help further lock down and what methods work for decreasing variability. And I worked on controlling and manipulating more variables. So I worked on like controlling when the injection happens of my internal standard or of the compound of interest, controlling temperature a little bit harder, controlling salt concentration, sonication times, and all of those stuff has major impacts on the end result. I've been conducting tests with known mixed compounds. So I've tried. I may have tried. I'm not sure if I'm going to do this, but I may have tried mixing beta-ionone and 3-octanol in solution, and then in doing that, I was able to get to see whether or not they were coming off in similar ways or different ways. So that would give me a good idea of whether it's a sample prep that's affecting it, and it's like, or if it's the machine peak area not working, or maybe it's just not reliably gathering on the fiber. But if they're picking up or being picked up at the same rate, then the fast SPME method might have more credence to it. I could use the average between the two and then use that for regression up. And then I'm also information gathering. So I looked at a lot of papers. And I condensed all the information and developed methods based on all the information I gathered. And I also applied a lot of the research into my development of a method and the math findings that I have found into development. So I've been using all of this stuff. Like, one of the major things that I found this semester, at least, was the injection happening after, well, just right before equilibration is a really big factor, because having the 3-octanol in the sonication step may have affected the amount of material that was in the end result, because some of it might have been able to leak out, because the sonication process creates an equilibrium faster, and that equilibrium could have been leaking out of the septa, it could have been sticking to the glass, it could have been doing something weird while that was happening. So injecting them just before equilibrium and letting the agitation create an equilibrium might have been a faster and better method. So the future direction of this project, that from the spring of 2023, is to create a relative concentration graph. So eventually being able to attach concentrations to all of the known data points by either spiking it with an internal standard, which is generally frowned upon the community, but what they do is generally they run another sample and they try to get the same peak area for a compound, and then that gives them, or they determine the concentration of one compound and relate it to all the others. That would be a starting step, and then to nail it down, you could do serial additions to get better concentrations and see if they line up from what you expect. Using this data of sampling to create domination of dogs. So kind of being able to tell what compounds indicate dominance and like what ratios of compounds indicate dominance. And then seeing what compounds are present in dog urine would be very helpful for understanding how they communicate and like seeing what like health effects can have on dogs. We might be able to get some of that too, seeing precursors of like what stuff is detected, like what compounds are indicating what. So the conclusion is solid phase microextraction of the headspace is a useful analytical technique that needs more support, it needs more testing, and it needs more information, because right now there's not a whole lot of widely available information on methodology, how tests are run, and like general support for this method. I think if this method was more widely available and more widely used and had more general knowledge, that it would be a more reliable method and could really help students and our project especially get on its feet. And that this analysis technique specifically shows potential for our project. So that this is really useful. This is a really cool technique to get into, and it's really interesting because, at least for me, it's so interesting to see such a simple theory, but and see the results and see how complicated, like you can take a really complicated effect, an idea, and then really boil it down to like you're literally just collecting vapors on a fiber and then baking them off. That's the summing it all up. Then in reality, you're like actually manipulating all these factors and to optimize the amount you get in the headspace, and it's really cool. So in this project, I would like to acknowledge Dr. House, especially. He's been very helpful for this project. I'm sure you've met him. I'm sure that if you're seeing this, you either found it on YouTube or he redirected you towards this video here. I'd also like to thank the University of Wisconsin undergraduate research program. They provided us many grants, and these grants have been helpful for these fibers and different aspects of the project that needed funding. And I'd also like to thank the Alexander and Marcia Orsolini Discovery Endowment, for they helped me this most recent spring 2023 to get the funding needed to buy the fibers. They covered like 120 or so dollar, 120 120 $50 on that final purchase, so that way we could actually afford the fibers. So this is the works cited page. This is some of the works that I used to create this project, and some works that I think would be pretty good to pair along with them. I do believe that there is a document that you can ask for that actually has more applicable and gives a little bit more depth and like a little bit like an annotated bibliography. It may be included in the description, or you can email Dr. House and he can give them to you. That would also work. And then that leads me to question or comments. If you have any questions or comments, please don't be afraid to ask about this project. We all are very interested in it and would love to have more people working on it with us, and would love to have more talented people learning and experiencing this undergraduate research. Thank you all. James Anderson out.